If the universe is constantly moving, why doesn't the night sky change? Right now, as you watch this video, you are hurtling through outer space at a mind-boggling speed. You aren't sitting, you aren't standing. You are flying on a cosmic spaceship called Earth. Our planet is spinning on its axis at over 1,000 miles per hour at the equator. At the same time, it is racing around the sun at about 67,000 miles per hour. The sun itself is rushing around the center of the Milky Way at a staggering 500,000 miles per hour. And our entire galaxy is moving through cosmic space even faster. We do not stand still for a single second. And yet, when you step outside at night, the starry sky looks completely familiar. The same constellations, the same patterns, and the North Star is always in its usual place. Why? If we are moving at such terrifying speeds, shouldn't the stars smear, the constellations distort, and the cosmic picture change right before our eyes? The answer introduces us to the first great paradox of physics. To understand why we feel absolutely nothing, we have to look back to the 17th century and a brilliant Italian scientist named Galileo Galilei. Galileo proposed a famous thought experiment, known today as Galilean invariance. Imagine you are locked inside a windowless cabin deep below the deck of a massive ship. The ship is moving smoothly, at a constant speed, without rocking. If you drop a ball, it falls straight down, just as it would on dry land. If you watch fish swimming in a bowl, they move effortlessly in all directions. Flies buzz through the air, and not a single one of them is pinned to the back wall of the cabin by the ship's forward motion. Without looking outside, there is absolutely no experiment you can perform inside that cabin to prove whether the ship is moving or standing still. Why? Because the air, the ball, and the ship all share the exact same constant speed. Earth is that windowless cabin. We don't feel the 67,000 miles per hour because our atmosphere, the mountains, the oceans, and your body are all moving together in perfect harmony. Space has no air resistance to push against us. But what happens when we look out the window? What happens when we look at the stars? The cosmic picture changes beautifully, but its scale makes this motion completely invisible to us. Imagine driving a car down the highway at 60 miles per hour. If a tree stands right by the road, it flashes past in a split second. If a mountain is visible in the distance, it barely seems to move. And if there are clouds on the horizon, you can drive for hours, and they appear to stay perfectly still. Now, let's blow up the scale to a cosmic level. The closest star system to us, Proxima Centauri, is about 4.2 light years away. That is roughly 25 trillion miles. 25 trillion miles. When Earth travels about 584 million miles in its orbit over a year, that sounds like a massive distance. But compared to 25 trillion miles, it's a microscopic step. It's like moving a fraction of a millimeter while standing half a mile away from an object. You moved, but your viewing angle stayed exactly the same. This is why the constellations seem locked in place. In reality, stars are moving, and they are moving fast, flying at dozens of miles per second relative to us. But because of the cosmic gulfs between us, their movement across the sky is agonizingly slow. Astronomers call this a star's proper motion. Over a human lifetime, a typical star might shift by just a fraction of an arc second. That is thinner than a single human hair viewed from several yards away. But there are exceptions to this rule. In 1916, an American astronomer named Edward Emerson Barnard discovered a tiny, faint red dwarf star in the constellation Ophiuchus. Today, it is famously known as Barnard's star. Barnard's star is a cosmic bullet. It has the highest proper motion of any known star in our night sky. It is rushing toward our solar system at a speed of 87 miles per second. Because it is relatively close to us, just about 6 light years away, its movement can actually be tracked over a single human lifetime. If you take a photo of Barnard's star today and compare it to a photo taken 18 years later, it will have moved across the sky by a distance equal to the diameter of the full moon. To astronomers, this is a screaming, blistering speed. But to the naked human eye, looking up without a telescope, it remains completely invisible. If even the fastest star in the sky takes nearly 2 decades to move the width of the moon, you can begin to see why the rest of the night sky looks utterly frozen. But if you could fast forward time by tens of thousands of years, the illusion would shatter. Constellations are not real groups of stars. They are just random projections onto the celestial sphere. The stars forming the Big Dipper, for instance, are at vastly different distances from Earth. They have no connection to one another. It's an illusion of perspective. In 50,000 years, the Dipper will look entirely different. In 100,000 years, its shape will be completely unrecognizable. There is another crucial factor. We are moving together with our local stellar neighborhood. The sun isn't flying through stationary stars. It moves among them. It's like a flock of birds in the sky. Individual birds shift around, but the entire flock maintains its grand structure. But what about the galaxy itself? We complete one revolution around the center of the Milky Way roughly every 225 to 250 million years. This is a galactic year. The last time the sun was in this exact position in the galaxy, dinosaurs were just beginning to walk the Earth. The entire existence of human civilization is just a tiny blink on this cosmic carousel. And while we cruise along our galactic orbit, our entire galaxy is on a collision course with a colossal neighbor. Deep in the constellation Andromeda lies the Andromeda Galaxy, a massive stellar island containing over 1 trillion stars. Right now, the Milky Way and Andromeda are pulling each other across the dark void. We are falling toward each other at a speed of 250,000 miles per hour. In about 4.5 billion years, our night sky will change in the most dramatic way possible. Andromeda, which today looks like a faint, blurry smudge of light, will grow to dominate the entire horizon. Its glowing, brilliant core will tower over Earth, casting shadows at night. Eventually, the two galaxies will crash. Stars will not collide. Space is too empty for that. But their gravitational fields will dance a chaotic, violent waltz. The beautiful spiral arms of the Milky Way will be ripped apart, flung out into deep space. The night sky will ignite with billions of newborn stars as giant gas clouds smash into one another, triggering an unprecedented cosmic baby boom. Over hundreds of millions of years, the two islands will merge into one giant, dead elliptical galaxy, nicknamed Milkomeda. But until that happens, gravity keeps our current sky safe and stable. Then there is the grandest factor of all, the expansion of the universe. Galaxies are flying away from each other. Space itself is stretching. Why doesn't this rip our night sky apart? Because the expansion of the universe is only noticeable across vast intergalactic distances. Galaxies bound by gravity do not drift apart. The Milky Way doesn't dissolve. The solar system doesn't expand. And even Earth stays the exact same size. Gravity locks local structures in a tight embrace. However, saying the sky never changes is wrong. There are subtle, ghostly shifts. The North Star wasn't always our guide. Due to a phenomenon called precession, Earth acts exactly like a spinning top that is beginning to slow down. As our planet spins, its axis gently wobbles, tracing a giant, slow circle in space. This cosmic wobble takes 26,000 years to complete one single loop. Because the axis is shifting, the point in the sky that we call the North Pole slowly moves. Today, our axis points directly at Polaris, our North Star. But it wasn't always this way. Around 3,000 years before Christ, when the ancient Egyptians were building the Great Pyramids of Giza, the axis pointed to a star called Thuban in the constellation Draco. The pyramids were meticulously aligned to a completely different northern star than the one we see today. And the sky will keep shifting. In about 12,000 years, Earth's axis will point toward Vega, one of the brightest and most beautiful stars in the night sky. Our descendants will look north and see a brilliant, blue-white beacon marking the way, while Polaris fades into a forgotten background. Furthermore, supernovas ignite and die out. In ancient times, Chinese astronomers recorded guest stars. Today, we know them as cataclysmic supernova explosions. The sky is alive. It is just operating on a clock that transcends the human experience. This brings us to a fascinating thought. We are used to thinking of motion as a synonym for change, but in deep space, speed means absolutely nothing without scale. You can fly hundreds of thousands of miles per hour and notice zero difference, because distances are measured in light years. We are passengers on a colossal ship rushing through the galaxy, but our windows show a frozen landscape, not because we are stationary, Chabia, but because space is simply too big. Someday, the distant descendants of humanity, if they exist hundreds of thousands of years from now, will look up and see a completely alien sky. And they will likely ask the exact same question: why do the stars look so still? The answer will be identical. The sky isn't frozen. It's just slow. Slower than our lives, slower than history, slower than civilizations. And in that lies its ultimate beauty. Every time you look at the stars, you are looking into the past. We are living in a roaring, dynamic universe, but it feels peaceful because its staggering scale turns cosmic speeds into a beautiful, eternal stillness. Next time you look up, remember, you are not standing under a frozen dome. You are screaming through the void right along with them. Thank you for watching this deep dive into the cosmic scale. If this journey blew your mind, make sure to subscribe. Share this video with a friend, and drop a comment below. If you could fast forward time to see the night sky change, which era would you visit? The time of the Egyptian Thuban star, or the future under the light of Vega? Until next time, keep looking at the stars.